boldly going where no science show has gone before. The Naked Scientists.
Hello, and welcome to this week's Naked Scientists, and that's with Helen Scales. Hello, Helen.
Hello.
Our marine biologist in residence. And Dave Ansell's also here, our kitchen science guru and physicist extraordinaire. Hi, Dave.
Hi there.
And also I'm Chris Smith. Now, coming up this week, a magnetic way to pick up cancer cells in the bloodstream. We'll find out how that works. Also, how scientists have seen the 4,000-year-old face of an ancient human, at least genetically speaking. And I can tell you for free, this person had dry earwax. How nice. Also, they say an elephant never forgets. But does it never run either? Well, we'll know in just a second because Helen Scales will tell us all. Helen.
Absolutely. Thanks, Chris. Also, this week it's our Science Question and Answer special. We will be solving your scientific problems. Coming up, why is Saudi Arabia blessed with most of the world's oil? Is IQ inherited? And what's the smallest thing we can see with a microscope? We'd also love to hear if you've got any questions for us at all. Details of how to get in touch are coming up shortly. Dave.
Thanks, Helen. And for this week's Kitchen Science, I'll show you a neat way to defy gravity. All you need is a raisin and a glass of fizzy drink.
I guess that's what you call popular science, Dave. Thank you. That's all coming up. If you'd like to get in touch with us, the email address is chris@thenakedscientist.com. You can also send us a tweet. On Twitter, of course, that's @NakedScientists.
The Naked Scientists Podcast. Powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
This is The Naked Scientist with me, Helen Scales.
I'm Chris Smith.
And I'm Dave Ansell. I'm going to kick off this week with a story about a new way to detect cancer cells. Cancer is caused by cells in the body mutating and losing their inhibitions and keeping on dividing and dividing. This causes a build-up of cells called a tumour. In the wrong place, this can be fatal, but more normally, the really dangerous part is when this tumour starts losing cells, which then take up residence in other parts of the body. This process is called metastasis. It'd be really useful to be able to detect these cells as soon as they get into the blood, but there may only be a few thousand of them in the bloodstream at any one time, and the amounts of blood you'd have to test would be really quite large. Now, Ekaterina Galanza and her colleagues have come up with an interesting solution to the problem. First, they inject tiny magnetic particles, which are chemically attached to a molecule that docks with a receptor on many types of cancer cells. This means that the cells get covered with lots of these magnetic particles. They then put a large magnet near a blood vessel, which attract these magnetic particles. Therefore, as the blood flows past, you get more and more cancer cells building up right next to them. They then fire laser particles into the blood vessel, which is absorbed by these particles, heating them up. They expand, which creates a sound which they can detect.
Oh, wow. So not only can you find the things using sound and magnetism, but you can also quantify them, because presumably the more that there are there, the more sound you're going to get.
That's right. So you can get some idea of how much there is. They actually did some experiments, and they found out with mice, and they found out depending on how bad the cancer was inside the mouse, that produced a bigger and bigger signal as they went through. They also got a better idea whether the cells they were detecting were cancer cells or just random other things which it stuck to.
I was going to say, because one major problem is non-specific binding. If this thing locks onto a cell that isn't cancerous, you're going to get the impression that there are lots more cells there than there really are. So how do they get around that?
Well, there's two things. One, if it's not locking very well, there isn't a very strong magnetic attraction, so they tend to wash away with the blood flow. And also, they've used little gold nanoparticles which absorb a different colour of light and attract to another docking station on cancer cells. So if you see both the magnetic nanoparticle signature and the gold nanoparticle signature, then you've got a much better idea these are definitely cancer cells. They've managed to detect them in mice so far, and they think it may be practical to use them in humans in future.
I did see something very similar when people were doing this for melanoma, the cancer which is derived from melanocytes, the skin cells that make black pigment in the skin. Very aggressive form of cancer, but they were using the fact that you could quantify how many melanoma cells might be going around in the bloodstream if these cancers are going to spread by firing a laser into the cells, and because the laser is soaked up by the melanin, the dark pigment, but not by red cells or white cells, it makes the cell get a bit bigger because it heats up, and this makes a little shockwave that you can hear as little clicks, and so you can work out how many melanoma cells are going around the blood.
Yeah, it's basically the same idea, but for cells which aren't already a funny colour.
Thank you, Dave. Now, let me introduce you to someone who's 4,000 years old. No, it isn't my geology teacher, just joking. This actually is a wonderful paper. It's in Nature this week, and scientists have actually come face to face, at least genetically speaking, with someone who, unfortunately, no longer has any descendants. This is an individual who was one of the Sakak people, who were one of the first inhabitants of what's Greenland today. And researchers have managed to perform a complete genetic sequence of this individual using traces of hair that turned up in an archaeological dig. And this dig dates from between about 4,000 and 5,000 years ago. That's the stratigraphy that they've got there. And what they were able to do is to find some hair samples which were mixed up with some bone. And hair is, it turns out, quite a good way of getting intact DNA out. And so they extracted DNA from this individual and have sequenced him genomically, and then done a trick called defining single nucleotide polymorphisms, SNPs, or SNPs for short. Long word, but what this means is they're like genetic signposts or flags along the genome, and they single out specific genetic hotspots that tell us about the genetic sequence either side of where they are. And because modern-day populations inherit all of the same SNPs, you can ask, well, what SNPs has this person got in common with modern-day populations? And that tells you two things. One is, who is this person who they found from 5,000 years ago related to? And also, what did he look like? We know it's a him because they've sequenced his DNA and we know it was a he. But the interesting thing that emerged was, first of all, we know that he was very short in stature, which is consistent with someone living up in the cold, frozen north. He also had very brown skin and dark eyes, very thick, wiry hair, a tendency to baldness, in common with many men, and also had dry earwax. There are two different polymorphisms types or genes that cause earwax. There's one type of wet earwax and one type of dry earwax, and he was of the persuasion that had the dry earwax. And that is interesting because that tends to associate with people who are from the east. And therein lies an interesting story, because people thought this tribe of people got into Greenland because they spread there from neighbouring areas of Inuits who were in that area already, and also in the Americas. Those people got there about 13,000 years ago. This person bears no genetic resemblance to those populations at all, much more closely related to people from Siberia. And so what this is telling scientists and archaeologists now is that there was a second migration of people into Greenland, what they call the New World Arctic. About 5,000 years ago, these people must have trekked out of Siberia, gone across the Bering Strait, crossed North America and gone into Greenland. And the sad news is he doesn't have any descendants that we know about still alive today. But there we are. It's amazing what the power of genetics can do now to tell us about what people were doing 4,000 years ago and even what they look like.
Extraordinary. Looking back into the past with these modern techniques. Well, I'm going to move things on to the animal world and the fact that it's often said that elephants can't jump. But can they run, or are they only able to walk? Now, that's a bit of a scientific conundrum that hasn't really had an answer until now, with a new study that reveals that they actually do a bit of both. And it turns out that they're extremely efficient for moving these enormous bodies across the earth at quite remarkable high speeds. Well, this is all thanks to a team of researchers led by Norman Hegland from the Catholic University in Louvain in Belgium. And we now know that when it builds up speed, an elephant's front legs trot while its back legs seem to walk. Now, ridden by their handlers at the Thai Elephant Conservation Centre, 34 rescued Asian elephants ranging between an 800-kilo youngster to a 4-ton adult were filmed as they were walked and charged along an 8-metre platform, and on the base of that were fixed plates to measure the forces being exerted with each stride of these huge elephants as they lumbered along. Now, what the team did was they tracked the elephants' shifting centre of mass and assessed how they transfer their energy between strides. And Hegland and his team discovered that at low speeds, elephants walk with extremely great efficiency. For every kilo of body weight, they use 60% less energy than we do, and 97% less energy than mice do. So they may be huge, but elephants are extremely efficient at getting themselves around the place. And the key to that efficiency lies in their stability. They always have 2 or 3 legs on the ground at any one time. And they also stride much more rapidly than perhaps we would expect. And this produces this fast, stable movement at slow speeds. Now, when most animals speed up, there's a point when they stop walking with a smooth pendulum-like motion and they start running. And this really involves bouncing up and down, storing up and releasing energy in springy muscles and tendons. a bit like on a pogo stick. I don't know if you ever had a go on one of those. I used to have one. It was great fun.
Kept falling off every time.
And,
the most amount of jumps I managed was about 10, I think.
That sounds pretty good to me. Anyway, so that's essentially what you're doing when you're running, is you're bouncing and using that energy, storing it and releasing it as you're going. And often this involves part of a movement where your body completely leaves the ground. Now, elephants don't do that. They can't jump. They don't actually ever leave the ground. And at high speeds, it seems what they're doing is that they're actually employing a combination of walking and running. As their weight transfers from side to side, they keep their centre of mass relatively steady. That's what this study showed, was they kept their centre of mass very steady, with their back legs really walking along at this steady rate. But their forelimbs were trotting and bouncing a little bit forwards. And it's almost like they're trying to shift gear and start running, but because of their immense bulk, these huge elephants don't quite manage it.
Thanks, Helen. Now, NASA has just launched a new satellite to study the Sun. Now, the Sun is the source of over 99.9% of the energy arriving at the surface of the Earth. And it's a very active place with giant solar flares and complex weather. This weather can hurl giant lumps of plasma called coronal mass ejections out into the solar system, knocking out power systems and satellites over 80 million miles away on Earth. Plus, we're just starting to understand the ways that solar weather can affect the weather on Earth. So NASA's launched this new satellite called the Solar Dynamics Observatory. It's designed to view the Sun continuously at a higher resolution, at a higher rate than ever before, take a spectrum of the Sun more than once every 10 seconds, and measure the magnetic field on the surface of the Sun continuously.
Is this an airborne, as in space, observatory?
Yeah, they've had to launch it into a special orbit because it's going to produce such an immense amount of data. It's producing about 1.5 terabytes of data every day, which is about 150 megabits a second, which doesn't sound that impressive on Earth, but getting that data down from space into Earth is very difficult. So actually have it orbiting in a geostationary orbit directly over its base station in America. And they've had to alter that orbit a bit so it doesn't get behind the Earth too much, so it can see the Sun all the time. And hopefully it will let us get a much better understanding of the Sun over the next few years as the data comes in, and we'll be able to understand how the solar weather actually works.
How will they be scrutinising what the Sun's doing? What sorts of measurements is it making and how?
Well, in the Sun, you get these things called solar flares and coronal mass ejections. Basically, the Sun is a great big ball of plasma. You get great big magnetic effects, which curl this plasma up into tighter and tighter knots, and eventually things seem to break and release this huge amount of energy. So looking at these things as they're forming in the optical region, in the ultraviolet region, actually measuring the magnetic field using various clever techniques.
So more than just a giant telescope, this is actually doing a whole range of different measurements of a whole range of different things for a long period of time.
Yeah, it's got 3 or 4 different telescopes on it. They want to keep looking at it so you get a good set of data over a whole period of the Sun's activity over 11 years.
Thank you very much, Dave. Helen?
Well, I'm going to take things right back down to earth again and ask you if you've ever tried running along a beach. And if you have, you'll know that on soft, dry sand, it's really difficult to do, and you keep on stumbling and falling over with the grains of sand shifting.
Well, if it's the beach at Southend, it's largely mud.
OK, sandy beaches, that's what I'm talking about. And sea turtles know only too well the perils of sandy beaches, because after they hatch, the turtles have to emerge from their nests and run the gamut of the beach down to the waves. And even though they spend just a few brief moments on land, baby turtles can move with remarkable speed across sand, even if it's loose and slippery. The question is, how do they do it? Well, it turns out that newborn turtles use their flippers to produce small blocks of compact sand, which act like a solid, allowing the turtles to propel themselves rapidly across the beach surface. Now, these findings are published in the journal Biology Letters by Daniel Goldman and colleagues from the Georgia Institute of Technology in the US. Now, last year, Goldman and his team built a creature called Sandbot, and that was a simple robotic creature that helped them understand how real animals cope with walking across soft sand. Now they've turned their attention to turtles, and the team, on a rather lovely assignment, went down to the beach at Jekyll Island in Georgia, and they were armed with a mobile laboratory, and they worked with the Georgia Sea Turtle Centre, and together they took high-speed film of hatchling leatherback turtles crawling along a trackway, and they covered that in loosely packed sand. What they found was the high-speed film revealed that the flippers pushed into the sand at precisely the right angle and force to build up these little blocks of compacted sand. and they could then push against those, generating a thrust to move themselves forward. And what this really is just showing us is that animals have evolved really elegant biomechanical solutions for these physical problems that the natural world throws at them. And to build a robot that can do the same thing requires really intricate laboratory experiments. So, meanwhile, the turtles have come up with their answer without really even having to think about it, to get their way across the beach from nest to sea and back again. And it's a mode of transport that scientists are just beginning to understand.
And presumably also want to borrow, because if we can work out how they do it, which they now have, and it's very efficient and effective, we could use it too, presumably. I should think so. If we want to send probes to Mars, clambering across all sorts of terrain, it would be useful too. But I think go turtles, fantastic, that they've got such clever ways of surviving in all different environments. Thank you, Helen. Now, a few weeks on from what happened in Haiti, the earthquake, of course, the whole situation there is still making news because of the sheer scale of the devastation. We'll hear more in a little while about how technology, and specifically the internet, can actually help to coordinate the aid effort. But what about the actual earthquake itself? What are scientists now beginning to learn from observing the land as it now is following the quake? Well, James Jackson's Professor of Active Tectonics at Cambridge University is with us. Hello, James.
Hello.
Welcome to The Naked Scientist. Tell us a little bit, if you can, about how scientists are now beginning to follow up what's happened in Haiti to try to understand more about what caused it in the first place and what's likely to come in the future.
We have a range of tricks now we can use to really do a forensic job on what happened in these earthquakes, wherever they are. Some space-based techniques, one of which is called radar interferometry. And all we use here is satellites which pass over the Earth and send a radar beam down to the surface of the Earth, and it reflects back to the satellite. This is the way people are used to hearing about radar to monitor aeroplanes or to ship at sea, to look at other ships at sea. By just sending a beam out and measuring how long it takes to come back tells you how far away that object is. Well, what these satellites do is pass over the Earth. They can take an image of the ground before the earthquake, take an image of the ground after the earthquake, compare the two, and see how the ground has moved between those two images. And we can do this now fairly regularly over most of the land surface of the Earth, and we can measure how much the ground has moved to an accuracy of a few centimetres. That doesn't sound, maybe it sounds a lot or a little to you, I don't know, a few centimetres, but the actual signal in the earthquake, the amount the ground moves in an earthquake like the Haiti one, is between 2 and 5 metres. So the signal-to-noise ratio is fantastic. It's very easy to see this. There are various problems with it, of course. The satellite itself is in a polar orbit, which means it orbits from north to south, and the Earth rotates underneath it. So you can imagine the satellite making a track across the Earth, and every time it goes round, the Earth has spun round a little bit more, so it makes a track over a different place. So the satellite only repeats over the same track about every 30, 40 days, something of that sort.
Which is why we've seen this little delay between the earthquake happening and now we're getting the data.
The data will come through. But not all satellites are the same. There's another effect we have to watch out for, which is the satellites were not designed to do this. So the satellites which are up there were mostly designed to monitor, in fact, the sea surface, because what you can monitor very easily and accurately is the height of the sea surface anywhere, and that is how you monitor things like the El Niño, the big weather effects, which are the real reason for putting those things up. So they were designed to look at the oceans, and you have a particular wavelength for doing that, which is optimal, which is about 5 centimetres for the sea surface. That's actually not very good for land, because it scatters off things which are about 5 centimetres in size, like leaves on trees. And places like Hispaniola and most of the Caribbean is covered in jungle, and that's not very good. So there is another satellite which has a longer wavelength, about 15 centimetres, and this is good. It sees through trees, but it doesn't repeat quite as often as the other ones, and so we've had to wait quite a long time to get this. But we now have some images of
I was going to say, you've now got the data, so what is this showing, and what can we learn from it? What should we now, or were our initial suspicions about what happened actually correct on the basis of what these satellites are revealing?
Yes, because there are other ways we can get it. We also have really pretty skilled now at using seismology, which is the sound that comes out of the earthquake to say what's happened, and we can use GPS, which is the precise movement of points on the ground, which is also monitored. It's the same technology used for sat-navs in cars, but actually rather more precise. So these things combined together are very much more powerful than each one on its own.
What are they revealing?
They're revealing precisely what we will find out in Haiti, or what we know now, is the length of the fault which moved, how much it moved, where it moved most, what's the distribution of slip along that fault, and how has the ground moved as a response to that earthquake. And why that matters, you might think, who cares after the earthquake's happened? Why should you do that? What you see is the ground moves. It moves up and down and sideways a few metres in this earthquake. But if it does it hundreds of times in hundreds of earthquakes, it produces the landscape. And so what you learn about is the relation between the landscape and the way these faults move. And then you can recognise signals in the landscape which tell you about these faults before they move. So you can actually go to a place and say, yes, I know why the land looks like that, because I've seen it before somewhere else. And that is what saves lives. It's that step, which is now fairly routine in places like California and Japan, which allows the engineers to know what they're up against and design things that don't fall down.
One snag, of course, is that everywhere on Earth is different, or you could argue everywhere is unique to a certain extent, so what goes for Haiti may not necessarily go elsewhere. So there will be a degree of geographic specificity, won't there, and therefore you need to have a long-term data set, I suppose, in order to get close to understanding how that bit of the Earth's surface performs and behaves.
The circumstances are different. So Haiti is covered in jungle, Iran's covered in desert, which is much easier to see things. So it's the way the faults move are not very difficult because they're obeying pretty basic laws of physics which we understand at that level. We understand what happens if you move a fault that size, the way it moved. It's maybe hard to see the signals in the landscape because they're not preserved in places that rain very heavily or covered in ice or snow or so on. It's harder to see than in a desert. So that's why we do these things all the time, because you're right. You build up a data bank of experience, essentially, where you see bits of the story in some places, but you recognise the bits you can't see because actually you've seen them somewhere else.
James, thank you. We'll just leave it there. Thank you very much. That's James Jackson, who is a geologist at Cambridge University. We've actually asked him to stay because there's a question on the way which is right up his street.
Lifting the lab coat on the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith, me, Helen Scales, and Dave Ansell.
If you want to get in touch with us here, then you can, of course, drop us a line on email. It's chris@thenakedscientist.com, or send us a tweet @nakedscientists.
Well, coming up shortly, we'll be having this week's edition of Kitchen Science. So we thought we'd just ask Dave to tell us what are we going to do this week.
Well, this week's experiment is incredibly easy. All you need is some fizzy drinks, so something that's ideally a clear fizzy drink, so something like lemonade would be ideal, a big glass or a big jar, and some raisins. Just pour out a big glass of lemonade, chuck in some raisins, and see what happens.
Sounds very simple indeed. So I think you should be able to try that out at home. If you can get yourself some lemonade, grab some raisins or currants, will they do as well?
Currants,
any kind
in
of
fact,
dried
even
fruit?
Pasta works quite nicely.
Even pasta works. Oh, perhaps that gives a hint as
Very
to
European.
what might be happening. Have a go and let us know what you think might happen. Chris@thenakedscientist.com.
Thank you, Helen. David's on the phone. Hello, David.
Hello,
Welcome to The Naked Scientist. Good to have you with us.
and it's good to be on.
Tell us about what we can help you with.
Basically, my parents are both fairly knowledgeable and have the ability to retain information quite well. And I seem to take after them, not being too big-headed, obviously. I was wondering, is this passed down genetically?
The nature-nurture debate is what I guess you're asking. This is a really hard question to answer for a number of reasons, which is partly how do we assess and appraise in IQ, or intelligence quotient? Because there's a guy called Jim Flynn who actually was working in New Zealand at the University of Otago, and he's credited with noticing what's now dubbed the Flynn effect. And this is that he points out that if you look at IQ test results that go back over many, many years, the average IQ has been rising by about 3 IQ points every decade, which means that if 100 is the average IQ, an average person in the population with average IQ has an IQ of 100, that means that if you take off 3 decades worth of improvement, people would have been in the mentally subnormal category a few years back, which obviously they weren't. And so he makes the point that it's the way in which we measure an IQ which has to be considered as well. Some people just don't trust IQ tests, but if you assume that we do, what proportion of the IQ that you or I have is because of the way our parents brought us up, and what effect is due to the genetic legacy that we inherit from those parents? Well, there's one quite neat way of looking at this, and you can probably guess what it is, which is to look at twins, because nature has blessed us with a set of natural clones, identical twins, and also a set of twins, non-identical twins, which grow up usually in the same environment as each other, but they don't have the same DNA in common. So you can compare the two. And that's exactly what researchers have done in the past. There's a guy called Paul Thompson, who is at UCLA in America, and published a beautiful paper in 2001 in Nature Neuroscience. And what he did was to take 40 twins. So in other words, he had 10 identical pairs of twins and 10 non-identical pairs of twins, and they did brain scans on them. And they compared the fine structure of the brains in both groups of twins, and they found that identical twins had a really, as in 95 to 100% similarity in the fine structure of their brains. The non-identical twins were much less similar. Then you ask, well, in that setting, how similar were their IQs? And when they did simple IQ tests, they found that the identical twins, there was a significantly much stronger relationship between their IQs than there was between the non-identical twins. So it shows that there's something to do with the way in which the brain is wired up and connected that definitely contributes to how intelligent we feel we are, or that people measure us as being. So the best guess at the moment is that there is some general factor, some people dub it G, which is what gives you your intelligence, and this seems to have a genetic effect, and this has superimposed on it an environmental and nurture effect. So in other words, you have a genetic legacy which is then manifest according to how nature impacts on it. So if you have a good upbringing and a good genetic legacy, by good upbringing I mean a good educational upbringing, then you probably will fulfil your genetic potential. That's not to say everyone who has a very high IQ is going to fulfil their genetic educational potential, because they may just not get educated. So I think that the best guess is that it's about 50-50.
Okay.
Good to have you on the show, though. Thanks for joining us.
Thank you.
All right, take care.
Well, we have with us in the studio Professor in Earth Sciences James Jackson from Cambridge University, and we've managed to persuade him to stay on because we've had a brilliant geological question that we think he would be perfect in answering.
Hi, my name is Andrew Dunn. I'm calling from Dublin, Ireland. My question is, if petroleum is derived from ancient fossilised organic materials, then why do the deposits appear mostly localised in the Middle East?
So, James, what's your thoughts on that question?
Most hydrocarbons are from dead organic, well, they all are from dead organic material, and you need an astonishing set of circumstances to make oil out of these things and preserve them. Firstly, you've got to concentrate them somewhere where they're not dispersed or oxidised, which means in sort of swamps and marshes or lakes or something like that. Then you've got to heat them up slowly over a long, long period to cook them up to make oil, and then you've got to actually, when they make oil and start to buzz off, you've got to have some way of trapping them. Now, all these things, it turns out, happen on the margins of continents. If you stretch continents and try and pull them apart, what happens is they neck, and that's what the North Sea is. The North Sea exists underwater because Scotland and Norway moved apart about 100 kilometres, and they just stretched, it necked the North Sea, it got a bit thinner, and it sunk below the sea. And by sinking below the sea, it gets buried in sediment. Sediment just gets washed in, and all those dead bugs which were there get buried deeper and deeper and deeper and get gently cooked for a long time. Eventually, although the North Sea stopped stretching, had it carried on, it would have made a plate margin. We'd have got the edge of the continent, and Scotland would have been over by Norway, by America somewhere, and Norway would still be in Europe. And so the circumstances for making oil are very good on the margins of continents, especially the margins of oceans like the Atlantic Ocean, which is not a plate boundary. There are no earthquakes there. Now, what happened in Saudi Arabia is that happened to be on the margin of a huge ocean which separated Asia from the southern continent. So 100 million years ago, Africa, India, Arabia were all a long way further south from where they are now, and they've all moved north and bashed into Asia. One of those places is Saudi Arabia and Iran and Iraq. And so what's happened is the margin of that ocean, with the margins of Arabia and Africa and India, have all just popped up above sea level. So it's not that there's more oil there than anywhere else. There's loads of oil all the way on the other continental margins, but it's underwater. It's hard to get out, it's hard to find, it's hard to suck out. Whereas in Saudi Arabia, it's popped up nicely above sea level, thank you, and also in Iran and Iraq. So it's actually extremely easy to find. And it's more that it's convenient than anything else. But geologically, what you're looking at is say, the edge of Ireland, the western side of Ireland, which has just run into something and popped back up above sea level.
Brilliant. Thank you very much, James. Lucky old Arabs happen to be in the right place at the right time,
Yes.
and their oil is available. Thank you, James Jackson from Cambridge University. Thank you for answering that question. Helen, had a few things come in from you. Silverwing Benoit is listening in Second Life. Hello to everyone in Second Life listening to us live there. Wants to know how they made the elephants run in the study you mentioned. And Nat Spirit, also in Second Life, says those elephants running around probably caused the earthquake.
Maybe, indeed. Well, the key point was that these elephants were in a rehabilitation centre. They'd all been rescued from logging operations, I believe, in Thailand, because they're often used to go into forests and actually drag out trees that have been felled. These are all elephants that have been paired up with handlers. As long as they've been at this rehabilitation centre, they've worked with an individual person who gets to know that elephant and can handle them and really control them and understand their different behaviours and characters. And so they rode on top of them and presumably know how to calm them down or speed them up. I don't know if they give them a crack on the hind legs to make them giddy up and to go a bit faster and to charge. But these are people, I think they're mostly Thai people who really understand the elephants and were a key part in this study. It wasn't just the scientists coming in and messing around with the elephants.
Thank you, Helen. Elephants are pretty intelligent anyway, so I think it's probably not too difficult to train them. Dave, this one I think is probably coming your way. Hello, Brannigan.
Hi, good evening.
Welcome to The Naked Scientist. This is an interesting question, and it's definitely one for Dave. Tell him.
All right, basically the article title was, if mud is on the right side, the ball will go left, and they're referring here to a golf ball. Can you explain how this works? Because I can't seem to figure it out.
So let me just summarise this. When whacking a golf ball, if you just don't put any spin on the golf ball, you're saying if you just whack it and assume it doesn't spin, but one side of the ball has some mud on it, they're saying that it will spin away from the side with the mud. Have I got that right?
It will move to the opposite side of which the mud is on, yes.
Dave, what do you reckon?
So what you're interested in here is the forces on the ball. If you've got air going past the ball, the only thing that can touch the ball is air other than gravity, which we're going to ignore because it's not very interesting in this circumstances. So you've got air going past the ball, and so if there's going to be force on that ball, that air is going to get deflected one way or the other. If the air gets deflected to the right, then there's going to be an equal opposite reaction on the ball, and it'll go to the left, and vice versa. Now, what's going to happen if you put some mud on the right-hand side of the ball? Okay, you've got air going both sides of the ball. On the left-hand side of the ball's just as normal. The air's going to kind of stick to the edge of the ball and come round as far as it would do normally. On the right-hand side of the ball, you're going to get a whole lot of mud. It's going to be rough. The air's going to get all turbulent, and it's actually going to leave the ball earlier. So the air coming from the left is going to stick on the ball longer than air going to the right, which means overall the air's going to start moving to the right, which means overall the ball is going to move to the left.
So that's basically it. So it wasn't wrong then?
It sounds perfectly plausible. It sounds about right to me.
Brannigan, I don't think you can sue them. They're not misleading you.
Thank you very much.
It's a pleasure. Thanks for joining us on The Naked Scientist. Still to come on this week's Naked Scientist, we'll be finding out in just a second how crisis camps can help to direct the earthquake relief appeal in Haiti and how we can deploy resources into areas that need them more efficiently using the internet. Don't forget Dave's Kitchen Science Experiment. Dave, just remind us what you want everyone to do.
Get a fizzy drink, ideally a clear one, but it's not vital, and then throw some small objects, something like sultanas, pasta, something like that, in there and see what happens.
And we'll also find out how many batteries you could possibly connect in series, which is what Richard C. is asking us.
Keeping you abreast of the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith, Helen Scales, that's me, and Dave Ansell. Now it's time to join Mira St-Thillingham, who's been in London this week, to find out how technology can be used to organise aid efforts in the developing world.
For this month's tech segment, I'm going to be finding out how technology can be used to help causes such as the Haiti Relief Fund. And here to tell me all about it is our resident expert, Chris Vallance. Now, Chris, you've brought me to the lovely Lincoln's Inn Fields in Holborn to tell me all about this today.
Yes, I'm working down at the World Service for a little while, so nearby we're in Lincoln's Inn Fields. So yes, looking at Haiti and how technologists, developers, hackers can help with disasters like that. A group called the Crisis Commons have been organising what they're calling crisis camps around the world that bring together people with skills in programming and developing internet applications to look at how they can help in disasters. Now, you may think, well, actually, probably what people need is food, water, shelter, medicine. But there are tremendous logistical issues, and IT and technology can help solve some of those, from some of the most basic, such as mapping. I went down to one London crisis camp and talked to some of the people involved with that.
Hi, I'm Vinay Gupta of the Hex Europe project, and we're here at Crisis Camp London today. Crisis Camp is a forum for all the people who are interested in using the internet and technology to help out in Haiti, to work together with field NGOs, which are actually on the ground, and organising NGOs like the UNHCR to really try and produce a coordinated response. What we're doing is lots of work like mapping and reviewing software, making programs work, gathering data from all the diverse sources on the internet, and putting it together into something that the people on the ground trying to help the population or doing reconstruction can actually use on a day-to-day basis to make their jobs easier and more effective.
And this isn't the only one that's going on?
No, today we have 13 running in 3 continents. Last week there were 3, so my guess is by the end of the month there's going to be one in pretty much every major city that has a tech community.
Is tech really a priority when a disaster hits, though?
If you think about, if something happened in the UK, the first thing you're going to want to know is, can you get on the road from one place to another with a load of supplies? So how do you find out? In the UK, there's a government infrastructure which will figure that stuff out and then make it known to the responding agencies. But in Haiti, the government buildings are all gone and a lot of their personnel are injured or missing. So to very quickly try and figure out what's possible and what's non-possible, what the military calls road intelligence or RODINT, how do you do it? So you have some military folks who are flying drones over the area, and you take the data from those drones and then you manually look at the roads and then you mark up what's possible and isn't, and then you put that into a database and you push it down to the aid agencies. The weak link is the coordination between all the different agencies on the ground. If you've got 70, 80, 100 responding groups and very little telecommunications on the ground, getting this problem of how do you make sure that you don't wind up with 2 sets of water and no food in a specific location, that's an ICT problem. That's computers and communication, software and coordination. And Crisis Camp has the ability to deliver software to help with that.
Are the coordinating agencies interested in what you're doing?
Oh yes, absolutely. Crisis Camp is NGO-led. The Crisis Camp US folks are working directly with field NGOs to get a sense of the technology requirements, write specs, and then put that stuff into action in terms of, now let's go find a team to build the tool that this group wants. So there's a direct chain of accountability all the way to the field.
I'm Alan Jackson. I come from Aptivate, which is a not-for-profit IT organisation based in Cambridge. Today I've been facilitating the first crisis camp in London, and we've really identified a couple of areas of different projects that have been identified internationally that we can contribute to.
So what kind of people are attending this?
It's an interesting mix of people, actually. We've got some network engineers, we have some software engineers, we have usability experts, and we have people with domain experience, people who've actually lived in Haiti.
And what kind of things are you trying to build, are you trying to do?
One of the projects that has been sort of mandated from the international community, it seems, is to have a look at a website called ReliefWeb, which is a sort of coordination portal for relief work run by UN OCHA. And so we've got a team of usability experts and low bandwidth design experts who are looking at that site and creating a kind of plan for it, which they can sort of share with the community. One thing that we're conscious of is the quality of network connections. There are internet connections that you have, particularly in a place like Haiti right now. So one thing that we have within the team here is a high degree of design expertise in designing websites for low bandwidth, slow internet connections. So we're really kind of taking that approach to ReliefWeb and seeing what can we do in that space to make recommendations to that team to see if there's anything that we can kind of help them with.
Some of the people at a London crisis camp.
Now, Chris, this all sounds really interesting, but is this kind of technology and this bringing together of people really useful for situations such as Haiti?
Well, separate to the crisis camps, I actually had a conversation with a mapping expert who was talking about the importance to NGOs of some of the OpenStreetMap work that had been done in order to produce detailed maps of Haiti, because one of the problems was finding out where things are, actually getting aid to the right places, and to do that you need good maps. So that sort of thing really is useful. Obviously, as we've sort of said earlier, medicine, food, shelter, those are all top priorities, but in deploying those, sometimes you do need some technological support as well.
Chris Vallance talking to Meera Senthilingam, giving us an insight into how technological advances can be used to help coordinate the aid efforts in developing countries like Haiti.
Laying the facts bare. I say. The Naked Scientists.
This is The Naked Scientists with Chris Smith, Helen Scales and Dave Ansell, and it's our science call-in extravaganza. We're answering all of your science questions for you. Now, Helen, we give you all the best jobs on The Naked Scientists. You have all the best stories, and we also reserve for you all of the best questions. This one has been pre-recorded by someone because there's a bit of a time difference, and you'll see why. He's in Australia.
Hi, this is Harry from Brisbane, Australia, and I was wondering if humans are the only animal that needs to wipe its bottom. Thank you.
I don't know what you're trying to tell me here, Chris. Thank you very much indeed. Well, I'm going to try to keep this not too smutty, but it's a really good question, actually. Do other animals have to keep themselves hygienic in that particular area? And as far as I think we know, we haven't found any animals that actually have invented a tool for keeping themselves clean in that way. There may be jokes about bears and rabbits, but they are just jokes.
Isn't it called their tongue?
Exactly. I think most animals do actually just keep themselves clean by washing themselves. You know what cats can do? They've got that clever trick of putting their leg behind their neck and they're keeping themselves clean that way. And another thing I think some people with cats and dogs might have noticed their pets doing is something called scooting. Well, that's the name. I think a lot of the Americans perhaps have come up with this word scooting, which is dragging their ass across the ground. And often pet owners get quite worried about why their dog or cat might be doing this. And often it is after they've been to the toilet and they wonder if it's something connected to it.
They usually wait till they've got into the room with the best and most expensive carpet in the house.
There are various factors like that to consider. But veterinary surgeons really think that it's probably maybe a parasitic infection. It could be worms. They're feeling very itchy and they want to scratch themselves. It also could be an infection of something that's rather charmingly called the anal glands, which is what many predatory animals have. Either side of the anus, they have these glands which produce smell. That's what a skunk produces smell from. It's what makes a fox turd smell like a fox turd and a dog turd and so on. So they use that to mark their territory when they're defecating. And if those get infected, they can also be quite painful, and that's why dogs and cats can drag themselves along the ground as well. And if your pet does seem to be doing that, it's probably best to take them to the vet and get that sorted out. So no, I don't think any animals actually use toilet paper, but if they need to, they will keep themselves clean in other ways.
I did see a funny sketch once where a certain well-known brand of toilet paper uses puppies to advertise its products, and someone suggested that if you run out of toilet paper, you could substitute the puppy instead of the toilet paper, but that's kind of a different issue, isn't it? Thank you, Helen, for that very well-answered question. Doug's on the phone. Hello, Doug.
Hello.
Welcome to The Naked Scientists. What's your question?
I was wondering if there are materials that convert heat directly into electricity.
Okay, you can't convert heat itself directly into electricity because heat, basically, you can't create or destroy energy, but you can do useful work with it, converting it from one form into another, and the forms which they always convert to eventually has very, very disordered forms of energy, and heat is one of the most disordered forms of energy. But you can get useful energy, useful work, electricity from heat flowing from somewhere which is hot to somewhere where it's cold. We've been doing that for hundreds of years. It's essentially what a steam engine does. You're moving heat from a hot fire to the cold outside world. You can do this just by putting two different metals together. This is called a thermocouple. That produces a minute amount of energy, but it's quite useful for measuring temperatures. You can get much more energy out using semiconductors. Essentially, you build a diode, and the hot electrons can go the wrong way through the diode, and then they have to flow all the way around the circuit back to the other side. As they flow round, then they can do work. So you can generate electricity through flows of heat, but not from the heat itself.
Helen.
So we had a question from Steve in Romford, and who says that if the colour black absorbs light and white reflects it, why do people who have darker skin tend to live nearer the equator, whereas paler skinned people live further north or south?
Well, mankind evolved, first was produced, if you like, in Africa, what's probably now northeast Africa. That's where the first modern humans originated from. And it's equatorial. It's very hot. There's huge amounts of sunlight. So the risk there is that people will end up with ultraviolet radiation penetrating their bodies. Now, the first thing people think of when you say ultraviolet is skin cancer. But actually, skin cancer isn't the sole explanation for why people have black skin. because most people don't get skin cancer until after the age at which they would have reproduced anyway, and therefore it wouldn't really have any benefit to them to have black skin. In fact, why they have black skin is to prevent ultraviolet radiation breaking down the chemical folate in the skin, and folate is really important for the production of DNA. So in order to conserve their reserves of folate, people who were first evolving in Africa actually evolved to have black skin, because the common ancestor that we share going back in time with, say, chimpanzees and things about 6 million years ago, those animals all had pink skins, but they had fur to protect them. As soon as they became hairless, i.e. our early ancestors, they had to evolve dark skin to protect them from the sun. But then when they migrated north out of Africa and they ended up in high latitudes, like in Britain, where the sun is something we don't see very often around here, certainly in the wintertime, there's just not enough sunlight now, coupled with a dark skin, to produce enough vitamin D, which gets made in your skin, so people then became a bit vitamin D deficient. So we lost the genes that made us have black skin in order to produce more vitamin D. And the benefit of doing that is you have stronger bones. The downside is you're slightly more vulnerable to the ultraviolet in the sunlight, but as there's much less sunlight, it was a worthwhile gamble to take. So that's the reason.
There you go. Now let's go to the phones. We have Ufa live on the line. Hello, Ufa. What's your question for the Naked Scientists?
Hello. My question is regarding light. I understand that light is considered to be made up of both waves and particles. And as far as I know, particles are actual physical objects. So my question is, how is light able to travel through glass?
Okay, the first thing is that any solid object that looks solid to us is actually, there's huge amounts of space in it. Even an atom, the nucleus of the atom is about 100,000ths of the size of the actual atom. So there's immense amounts of empty space, and only a few electrons flying around the space. There's lots and lots of space for things to travel through. A light wave is actually quite big compared to the size of an atom. It's bigger than an atom. So so it's a quantum mechanical object. It's kind of a particle. It's kind of a wave. You can think of it as a wave which only arrives in particles. It's not really something that which we have a handle on. So it's a lot easier to think of it in a wave in this circumstance. And the only thing which will stop a wave is something which will absorb it or scatter it. And in something like glass, there's just nothing there to absorb it or scatter it. So it just carries on going in a straight line.
Ufa, thank you for your call. I understand you're in Manchester, but you're originally from Denmark.
That's correct.
What a great name. Where in Denmark?
From Copenhagen.
Everyone, all the best people are from Copenhagen, I've heard. All right, thanks for joining us on the programme.
Thank you.
Ellen.
Right, well, we have a bottle of lemonade, we have a handful of raisins, and I think that means it's time to find out what's happening with this week's Kitchen Science, so I shall hand everything over to Dave.
Okay, so I'll open the lemonade. I'll pour it into the glass. Actually I'm using a jar. I'm going to try and pour it so as not to lose too much of the fizz, so I'll pour it in gently.
So he's pouring it down the side of the jar, the glass. Good, a nice, whole good canful there I think he's got. Excellent.
Okay. And now we'll just chuck in some little currants.
Okay, so they've mostly sunk to the bottom, but... Oh goodness, what's going on now? They're popping back up to the surface and are covered in lots of silvery bubbles. They look very pretty, actually.
I could just interject here. We have heard from Red Lace Celine, who I think is in Second Life, who says they took some California raisins, seedless ones, if that's significant, Dave, and they dropped them into Abbott Ale, so the slightly more upmarket version of the experiment. They said they went up, down, up, down, up, down, up, down, and blah, 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 blah. Clive Munson said they sunk to the bottom, got a coating of bubbles due to, he points out, nucleation, rose to the top, lost the bubble, dropped again. Said he's actually seen Paul Daniels do this and wrote about it in a magic book in the 1980s. So there you go, a bit of Paul Daniels magic on the Naked Science.
Magic science or vice versa. Yep, so basically what's happened, they're exactly right. In lemonade, the reason why it's fizzy, the reason why it tastes some part of the reason why it tastes acidic is there's lots of carbon dioxide gas dissolved in there. It's been dissolved under pressure, so you've got lots of extra carbon dioxide in there. As soon as you release the pressure, that wants to escape. It does that at the surface just by sort of evaporating off, but when it's deep down, it wants to form bubbles. It can't form bubbles in the middle of the liquid very well because there's a force called surface tension which tends to collapse them and crush the very small bubbles. So you need to get big enough to start with. If you give them an object to start on, it's much easier. So bubbles tend to start on the both the raisins and on the glass itself. And so slowly the bubbles get bigger and bigger and bigger as more carbon dioxide comes out of solution until eventually the raisin floats up to the surface and they pop and then they sink back down again. And it's really quite...
It's really mesmerising, I have to say. Their kids, they're still going, and I think I could watch them for ages. They're alive. It's amazing. It's wonderful, and they're very pretty too. I like it. Silvery bubbles, gorgeous.
Yeah, it's related to the trick where if you get some sugar and drop it in your mate's glass of Coke, the whole that gives you lots of nucleation spikes, so you get lots and lots of bubbles, and the
you
whole
used
stuff
to do that
goes
too.
all over the place.
But it's sort of the Mentos and Coke experiment is all based around the same thing.
Yeah, it's all
isn't it?
based around the same thing, nucleating bubbles so they can form more easily, those that you do it really, really explosively.
Because if you watch the bubble size as they rise up, they do actually get bigger as they go up through the glass, and it's nothing to do with pressure so much as that there's already a bubble there, which means it's much easier for it to gather more gas from the water around it on the way up, isn't it?
Yeah, it's really quite noticeable if you do the Mentos Coke thing, although you probably don't want to be close enough to see the size of the bubbles while you're doing it.
Indeed. Well, thank you very much, Dave. Look, we've also got a wonderful question here, which I think probably the pair of us could do a reasonable job on. So, and by the way, Dave's Kitchen Science experiment is on the web at nakedscientist.com/kitchen science. Have a listen to this, Dave.
Hello, this is Becca from Finland, and I would like to know what is the smallest thing that is possible to see with a microscope?
Okay, it depends on the kind of microscope. As we were talking about earlier, light behaves a bit like a wave. It has a wavelength. And it's very, very hard to see things smaller than the wavelength of the light because you essentially get interference effects. The waves interfere and it messes with your picture. So with not conventional microscopes, it's very hard to see anything less than the wavelength of light, which is about half a micrometer, so about a 2,000th of a millimetre. There are ways of doing things with light, which means you can get a little bit smaller than that using funky things called metamaterials, but they're really not common. If you want to get much smaller than that, you need to use something with a much smaller wavelength, and a common one to use is an electron, because although it's like a particle, it's also a wave, and the wavelength is much, much shorter, and therefore you can see much, much smaller things, and you can actually see kind of big atoms with a normal electron microscope. And other forms of microscope involve dragging a tip, it's called scanning tunneling electron microscope, and measure electric current going between your tip and the object, and you can measure down to definitely large atoms.
IBM iconically produced the letters IBM, I think it was 1990-91 time, by manoeuvring xenon atoms with a scanning tunneling electron microscope, didn't they? And I think I can't remember quite how many atoms they used, 40 or something, and it took them about 2 weeks to move these things around. But people were saying this is the future of computing. There was also a story that got published in the middle of 2008. It was by a researcher at the University of California at Berkeley, Yannick Meyer. And this was a wonderful paper because they actually were able to see hydrogen atoms. So I think that probably qualifies as the smallest thing you could see, because that's the smallest thing, entity, at an atomic level in the universe. The way they did this was they had a sheet of graphene, which is a single layer, one carbon atom thick of graphite, and they could drop molecules onto that surface and then scan across it with the scanning tunneling electron microscope and measure where it was interacting, the tip was interacting with the different atoms. And because the graphene is like a little pattern of chicken wire, it's very regular hexagon pattern, it's very easy to subtract that mathematically from whatever signature you pick up, so you can see any atomic species that were dropped on there. So they could see these little white dots that turned out to be hydrogen atoms. But if you put a big molecule, like a butane molecule that you burn in your lighter or something on there, you can actually see this zigzaggy chain of hydrocarbons. It's just absolutely phenomenal. You're listening to The Naked Scientists with Chris Smith, Helen Scales and Dave Ansell, and we're answering your science questions. Coming up in a second, Diana O'Carroll will be with us with our question of the week, which this week asks, can you send and receive a phone message in a black hole? No idea why you want to do that, but we'll find out the answer. Dave, in the meantime, how many batteries can you place in series, asks Richard C. He's in Belgium, says he loves the show, but he's wondering how many batteries he could connect together to increase the voltage. What would be the limit?
Okay, a battery basically got a little chemical reaction inside which causes, the conventional ones causes one end of the battery to be 1.5 volts higher than the other end, electric potential energy. So you can join batteries together and the voltage will get higher. I can't see any intrinsic limit to how you do that, if you keep on doing that and doing that and doing that, unless you get to the point where the voltage is so huge that you'll cause sparks from one end of the battery to Earth. So it depends how good your insulation is. Through air, you can cause a spark at about 1,000 volts per millimetre. So if you're getting into tens of that or millions of volts, then you could create sparks. I think the bigger limit is how much money you have to buy the batteries and how much time you have to join them all together.
There was a place in Alaska that I read about 5 years ago who they're having so many frequent power cuts, they decided that they would build a massive great nickel-cadmium battery to prop up the town every time there was a power cut. So they had, it was something ridiculous, like 13,000 NiCad batteries all linked up to produce mains voltage for a short while to sustain the town to overcome these power deficit problems.
Yeah, definitely. In the past there have been various research batteries which have been thousands and thousands of volts because it was the only way you could make these high voltages. Now we have easier ways using electronics.
Cheers, Dave. And very quickly, Helen, John Ewan says, do warmer waters attract more sharks?
Well, I believe that question came from someone who's been reading our website, and there's a fantastic article on there by Bruce Wright from a couple of years ago about how there are more sharks appearing in inland waters in Alaska. And that's one particular case that seems to be going on in a global scale. Last year, in fact, there were lots of news stories about shark attacks on the rise being linked to global warming. And really, there was no proper science backing that up at all. First of all, is there really an increase in shark attacks? Well, maybe, but not necessarily for any other reason that there's more people in the water and we're reporting more shark attacks. There's only about 50 to 100 every year, but when there's a spate that occurs perhaps, in a month or two, people get very excited and think, oh gosh, something must be going on. Yes, sharks do respond to temperature. There are various ways that affects them, and changing warming seas are likely to affect sharks. One thing in particular, a recent study has suggested that the Antarctic could become infested with sharks. There haven't been any sharks there for 40 million years, but as it's warming up, they could start moving back in there, and that could really affect the ecosystems in those areas. So, yes, sharks are affected by warming seas in ways that we're just starting to understand.
Brilliant. Thank you, Helen. Right, I've been dying to know the answer to this one for quite a while. Welcome, Diana, back to the studio.
Hello.
With this week's question of the week. My house is in something like a black hole for mobile phones.
Yes, that's right. This week it's all about how to call someone and tell them of your impending doom.
Hi, I'm Sophie from Chicago, U.S., and I'd like to know, is it possible to make a phone call from a black hole?
Would your cries for help make it through the event horizon?
I'm Andrew Ponson, and I'm a research fellow at the Kavli Institute for Cosmology. The short answer is no, but maybe you could receive a text message. So let me take a step back and try and explain. Basically, when you make a mobile phone call, the device you're holding in your hand is using radio waves to send your voice to the person at the other end of the call. Now, radio waves are just a certain form of light. We can't see it directly, but we receive it using antennae in our mobile phones and other devices. And because it's a form of light, just like any other light, it can't get out of a black hole. So you cannot send your voice out of the black hole. There's no way for you to have a conversation. On the other hand, light can certainly get into a black hole, and in the same way radio waves can get into a black hole. So if you were to adapt your mobile phone so it could just receive text messages without having to communicate to the network, it could just pick up the radio waves of the text messages, then you could actually receive a text message from your mum just before you died at the centre of the black hole.
Lovely. So no one can hear you scream from a black hole, but you could pick up a text telling you to pick up some potatoes the next time you go shopping. That answer was given by Andrew Ponson, and you can hear more from him answering your science questions and keeping us up to date with space science news in our Naked Astronomy podcast, available from thenakedscientist.com/astronomy.
And on our forum, Giza said that a long extension cord might be a solution to the problem. Warwick told us by email that no form of light can escape a black hole, as the gravitational pull is virtually infinite, but that there's also a theory that some other forms of energy might escape through the interactions between subatomic particles. Paul in Shropshire said that a phone call made from exactly the event horizon might hang around indefinitely, but he wasn't sure that anyone else would show up to hear it within a few 100,000 years. He thought perhaps the best idea was to leave a note when you are just about to enter the gravity well, saying, going down a hole, I may be some time.
Well, let's lighten the mood a little with a more radiant question.
Hi, Naked Scientist. This is Jacob Kemmerer from Virginia, USA. I'm currently snowed in right now, and I know that painting rooftops white would help cool cities. I was wondering if plowing snow would cause any global warming or add any additional heat to the Earth.
Will leaving the snow on the ground help us keep the world a little bit cooler? Let us know the answer by emailing chris@thenakedscientist.com or by writing on the forum at thenakedscientist.com/forum.
Thank you very much, Diana O'Carroll. And a wonderful question for next week. Dave.
Got a question here for you, Chris, probably, from Sammy. Why do sweeteners taste different to sugar?
Yeah, well, they do taste sweet, don't they? In fact, we talked about aspartame either last week or the week before, and that's about 200 times sweeter than sugar. And the reason people use it, of course, is to make things taste much sweeter, but without having to add additional sugar, because the sweetener molecule has got virtually no calories in it versus the large amount of calories that are in sugar. It fools the tongue into thinking things taste sweet because it locks onto the same chemical receptor, the docking station that recognises sugar, making it taste sweet, but in reality it doesn't actually impart any caloric contribution. The reason it also has other tastes is because it doesn't just recognise the receptor for sugar, it also binds other receptors as well, and that gives it those other tastes because it binds to other flavour receptors too. So that's why you get those other side tastes. Great question. Well, that, I'm afraid, is it for this week, so I have to say thank you very much to our wonderful production team, who is Mira Lingam, Ben Valsell and Tom Simpkins. We're back next week looking at how humpback whales have inspired a new type of wind turbine and how new inflatable wind turbines could be deployed high up in the atmosphere. Do join us if you can.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.